And now we're going to start talking about the details of glycolysis. Well, not so much in detail, more like an overview, and then I can look at this in detail before my test. But it's good to know this order, starting with glucose, ending up with pyruvic acid. Then we have all of these steps in between. Let's look at it a little more detail here. So, of course, we know that glycolysis begins with the phosphorylation of glucose, and we're using hexokinase here, and that the phosphorylation assures that the glucose will stay in the cell. And we talked about that. In glycolysis, some steps are reversible, whereas others are irreversible. And the big overview of glycolysis is, of course, as we've talked about, that it generates 4 ATP, but there is an energy investment stage where 2 ATP are invested, and so even though 4 are generated, we end up with 2 ATP. So let's talk about it in a little bit more detail. And continuing on, let's look at this first stage, looking at glucose and how hexokinase here, this enzyme, is used to remove one of the phosphates and transfer it convert it to glucose 6-phosphate. And we can remember, of course, with this OH group, we are able to add the phosphate, and so here we can see the added phosphate, and now it is, recognize it is a 5-carbon ring, and that because it has been phosphorylated, it cannot escape now through the GLUT4 channel. So this is our starting, and this is part of the investment stage. And continuing on, moving down here, we can see that we changed the carbon ring formation, and we move it around a little bit. What happens now is we have fructose 6-phosphate. We're changing from glucose to fructose 6-phosphate. Then we lose another ATP through this with phosphorofructokinase, and then now we have 2 phosphates here, biphosphate. We've now changed this to fructose 1,6,5-phosphate, the 1,6 referring to the positions. And now this is a very important step, so we need to just explain what happens in this section. This is a very important stage here. So we have fructose 1,6-biphosphate, but now it's going to split into dihydroxyacetone phosphate and glyceraldehyde-3-phosphate. And now the dihydroxide acetate phosphate is sort of a dead end. It's not really going anywhere, but you'll see later on this is our bonus. And we're going to, of course, this is going to be used to make the extra ATP. But we should take note that the glyceraldehyde-3-phosphate is the one that moves on and goes on to the next step. And in the next step, Glyceraldehyde-3-Phosphate Dehydrogenase, and dehydrogenase is the one, the enzyme that sort of gives you the hint when you hear that dehydrogenase. You know that perhaps NADH is going to be formed, and here we can see that NADH is formed here, and we know that NADH is going to be carrying electrons, and this is going to be used, but it's not at the moment not easily transferred. You cannot transfer this right into the mitochondria. So at this point, let's just remember that NADH is made here, and that in glycolysis 2 molecules of NADH are made, which will then go on to make 6 ADPs. But anyway, let's focus on the next step. So in moving on, after we made that NADH, we move down through the process, and now we've actually made our first ATP here, ADP to ATP with phosphoglycerate kinase, and then my mouse is not working, so we move down, and continuing on and moving on to pyruvate, we make 1 more ATP, so we have an investment of 2 ATP, so we lost 2 ATP, and then we made 2 ATP, so now we have 0. So we wonder where that other 2 ATP comes from, and that comes from the hydroxyacetone phosphate, which will then go through again, but this time, because there's already been the investment, you actually end up with 2 ATP. So there we have the 4 ATP that are made and the 2 ATP that are invested, with the result of 2 ATP. So continuing on, let's look at what we've made. Remember, we just said that this reactions in glycolysis would create NADH, and that it makes 2 molecules of NADH, and the reason is because after the split from fructose 1,6-biphosphate into dihydroxyacetone phosphate and glyceraldehyde-3-phosphate, glyceraldehyde-3-phosphate goes through and makes an NADH, but then dihydroxyacetone phosphate goes through again and makes another NADH. So that's where we get our 2 NADH. And looking at glycolysis, we have the yield of 2 ATP, and then we have 2 NADH, which comes down to 4 or 6 ATP. And remember that NADH, for each NADH, it makes 3 ATP, so 2 times 3 is 6. And it does say 4 or 6, so there is some movement here, some adjustment. So the main point here is that 1 mole of glucose will give you 36 to 38 moles of ATP. And in later videos I'm going to talk about pyruvate dehydrogenase and acetyl-CoA and how some of these other actors come into play. But for now, that's the basic energy yield from glucose oxidation.